Right. So for the workshop for heat, so the first question is about mixing two liquids initially at different temperatures, and you're asked to find the final temperature. And we've derived the equation in the lecture, so you can refer to your notes. And then the second question is practicing Q equals MC delta T and Q equals ML, and figuring out which equation to use. Is the material undergoing phase change or not? So I just wanted to point out something here, because the graph looks similar to what we've seen in the lecture, but it's a bit different in the way that the x-axis, so the x-axis is given in time. So the time when the heat is being added to the material. The y-axis is still temperature, which is the same as what we've seen in the lecture. So the x-axis is given in time because we are given the rate for which heat is being added to the iron sample. So heat is added at 5 joules per second. So that means heat added every second, or Q divided by time, or the rate. That means that every second, 5 joules of heat is being added to the liquid iron, right? And so so 5 joules per second means 5 joules of heat is added every second. Okay, so by looking at the x-axis of this graph, so the x-axis gives you the time. By looking at how long you're adding heat to the iron, you will be able to figure out how much heat you've added, right? So for example, you've added heat for 2 seconds, okay, then the total heat that was added was 10 joules, right? Because 5 joules is added every second, which means after 2 seconds, 10 joules would have been added to the iron sample. Okay. So I just wanted to point that out, because the graph is presented in a different way in the worksheet, but the analysis of the situation would still be the same. It's just you'll need an extra step of getting how much, getting Q, how much heat is added to the system by multiplying by how long, multiplying with how long you've been adding that heat to the system. Okay. All right. So I hope that makes sense. Okay, so you have now 20 minutes to look at the worksheet, and then at 11:30 we will look at the solutions to the problems in the worksheet. All right. Okay. All right. Okay. It's 11:30, so let's look at the solutions to these problems. Okay, so the first one, we have water. So it's the same substance, only of different amounts and different temperatures. So 100 grams at 10 degrees Celsius and 200 grams at 40 degrees Celsius, and they're mixed together. And we're being asked to find the final temperature. So we've seen during the lecture that so of course, heat will transfer from the 40 degrees Celsius water to the 10 degrees Celsius water, from hot to cold, until you arrive at the final temperature, at which case you're at thermal equilibrium. So the heat lost by the 40 degrees Celsius water will be gained by the 10 degrees Celsius water. And we've already derived the equation earlier during the lecture. So to find the final temperature of, let me just use black ink. To find the final temperature of the water that's mixed, you need the mass of the hot water times specific heat times the temperature the initial temperature of the hot water and cold. Just writing down the equation here. C hot plus M cold. Okay, right. So that was the equation that we derived in the lecture earlier. So we're given the mass. So make sure that you use SI units here. So you need to convert masses to kilograms. Notice how your masses are given in grams. So to convert to kilograms, right, you divide by 1,000. So 100 grams. 0.1 kilograms, and for the sorry, that's the other way, 100 grams is the cold water. And for the hot water, you have 200 grams. Okay, the specific heat of water is 4186 joules per kilogram per Kelvin. Okay, right, but notice how the specific, so it's just water, the cold and hot material is just water. So notice how the specific heat appears in all terms in the equation. Okay, C hot and C cold will be the same because it's the same substance, it's both water. And since the specific heat appears in each term of in the equation, we can factor it out, right? We learned last time that if something occurs in all the terms, you can factor it out, and essentially you have specific heat in the numerator and specific heat in the denominator. So effectively, specific heat will cancel out of your equation. Okay, so you have actually, if the two substances are the same, you have this simplified equation for the final temperature, which only involves the masses and the temperatures of the substances. Okay, the specific heat is not needed in the equation. Right, so special form just when the specific heat can cancel out. Essentially, you know everything. So we can substitute the values. So if you want, you can convert the temperatures from Celsius to Kelvin, right? So you have temperature of the cold, 10 degrees Celsius, add 273 to get the Kelvin temperature, and temperature of the hot, 40 degrees Celsius plus 273 gives you 313 Kelvin. Right, so essentially, you know everything. We can plug everything into the equation now. So 0.2 times 313 and the whole thing is added to 0.1 times 283 divided by the mass of the cold one, 0.1 plus 0.2. Right. Cool. And that should give you a temperature of 303 Kelvin. Or if you did that in degrees, 30 degrees Celsius. Right, are we happy with the solution for that? If you have any questions, just feel free to type them in the chat box, and I'll keep an eye on the chat box. And otherwise, I'll proceed to the next question. And yeah, you can always ask, and we can always go back to this question later on if you have anything you wanted to clarify. Cool. Otherwise, yep. So the next question, 1 gram sample of solid iron has an initial temperature of 20 degrees Celsius. So it initially starts at this point in the graph, and a constant rate of energy is input at 5 joules every second. And we're given this temperature graph. So as I've explained earlier, what we have in the x-axis is time, and what we have is the rate for which heat is added. It's 5 joules every second. Okay, so keep that in mind as we go through the questions, because when you need to find the heat that's added, then you have to consider how long the heat has been added for in order to find the heat when you're given the rate 5 joules every second. Okay, but the first question asks us to convert all quantities into SI units. Okay, so 1 gram, that's the mass. We have to convert that to kilograms. We've been doing that quite a lot now, so hopefully by now it's sort of automatic. You have to divide by 1,000, so that will be 0.001 kilograms. Okay. The temperature was given in degrees Celsius. So initial temperature 20 degrees Celsius, and the SI unit for temperature is Kelvin. So we need to add 273 to give us the Kelvin temperature. Okay. If you want, you can also convert all the temperatures in the graphs so that you already have the converted temperatures when you need them. So just adding 273 to all the Celsius temperatures will give you the Kelvin equivalent. Right. Okay, so you have that conversion there. Okay, so looking at the graph and just looking at section A, so region A here, we can see that heat is added over a period of 136 seconds. So we're going to the second question now. And as heat is added over this 130 seconds time interval, you can see that the temperature of the iron increased from 20 degrees Celsius to 1,535 degrees Celsius. So in this region, region A, do you think the iron is solid only, solid and liquid, or liquid only? right? We learned that when your object is only at single phase, any heat that's added to it will cause its temperature to change. So looking at the graph, you have there two regions, region A and region C, where the temperature changes. So that tells you that initially the iron started as a solid, and then the second region of temperature change is when it's all liquid and it has melted. So region A will be solid. Okay. Region B, so notice in region B, you're adding heat in the interval from 136 seconds to 190 seconds, but notice how the temperature of iron remains the same at 1,535 degrees Celsius. So do you think at region B, is iron solid or liquid, or both solid and liquid? Both, right? Yeah, because we know that when an object is undergoing phase change, then two phases exist at the same time, and therefore temperature will not change, because any heat added to the object will go into the phase change. So it's both solid and liquid. Okay. So that's region B, is the melting, is when iron is being melted, and therefore liquids, section C is when you only have purely liquid iron. So all of the iron have melted, and any heat that's added to it in region C goes into increasing the temperature of liquid iron. Right. Cool. The next question, so at what temperature did the iron start to melt? So meaning, what is the melting point of iron? Right, so by analyzing, the graph from the previous question, so we said at section B, that's when iron is undergoing phase change, and the temperature remains at 1,535 degrees Celsius. That means that's when, at that temperature, iron is melting. So therefore, the melting point of iron is 1,535 degrees Celsius, or that one, you converted that to 1808 Kelvin in the earlier question. Okay, so next, how long did it take for the solid iron to be fully melted from the time heat started to be added? Okay, so that's from the initial time, from the initial graph. Okay, so you're measuring the time from this point. That's the starting point. Right, so we've identified that section B is when iron is melting. Okay, and section C is when iron has fully melted, and therefore it's only just liquid iron, and you have this increase in temperature. So that means at this point, just before the temperature of liquid iron starts to increase, that's when you have fully melted all of the iron. And looking at the x-axis value, that's a time of 190 seconds from the starting point. Okay? So therefore, it took 190 seconds to first increase the temperature of solid iron from 20 degrees Celsius to the melting point, 1,535 degrees Celsius, and melt all of the iron fully until this point, 190 seconds, right? Okay, so I think so far the questions, we're just sort of reading the graph and trying to interpret what the graph means. The second question is where we now go into some detailed calculations. We're being asked in question E to determine the specific heat capacity of solid iron. Okay, so by identifying which regions the iron exists as solid, liquid, and both, we've seen that's region A is when iron is solid. Right, and the temperature of solid iron changes, and we've seen in the lecture that the heat added to iron that results to the change in temperature is given by this equation, Q equals mc delta T. Okay. But we are looking at region A. Okay. To find the specific heat, we need to find C. So we need to rearrange this equation to isolate C. C is tied to the mass and change in temperature via a multiplication. And so to undo the multiplication, we need to do the division, dividing by M and delta T. And we have to do that division on both sides of the equation. Right, and so we have specific heat is equal to the amount of heat that's given to the iron divided by the iron's mass times the change in temperature. Okay, so the mass, we know it's given 0.001 kilograms. The change in temperature we can read from the graph. So the temperature change from 20 degrees Celsius to 1535 degrees Celsius. So we can sort of write down what we know here. Change in temperature, that's the final minus the initial temperature. 1535 minus 20 gives you a change in temperature of 1515. Okay. Now to solve for the specific heat, you need to figure out Q, how much heat is added to iron. Okay. So as I've mentioned earlier, 5 joules of energy is added every second. Okay. But throughout the, by changing the temperature from 20 degrees to 1535 degrees Celsius, it takes about, it takes 136 seconds, right, to accomplish that change in temperature. So that means that Q, which is being added at 5 joules every second, should be multiplied with the time over which heat is being added, right? So for 136 seconds, you're adding 5 joules every second. Therefore, the total heat you've added will be 5 times 136 seconds, right? Does that make sense? Cool. All right, good. Thanks for the confirmation there. So 5 times 136 is 680 joules. Okay, so that's the amount of heat added over 130 seconds. And during that time interval, the temperature changed from 20 degrees Celsius to 1535 degrees Celsius. Okay. Right, so therefore we can solve for the specific heat of solid iron. 680 divided by 0.001 times 1515, giving you 449 joules per kilogram Celsius or Kelvin. Because it's a change in temperature, Celsius is the same as Kelvin. Cool. All right, the next question asks us to determine the latent heat of fusion of iron. So we learned that latent heat is associated to phase change. Okay, and we've identified that region B is when iron is changing phase from solid to liquid. So region B, solid plus liquid. Therefore, region B is what we want to look at when we're considering the phase change and the latent heat. Okay, so region B, where phase change is occurring, is just between the time interval 136 seconds and 190 seconds, right? It's just over this time interval. Right. Latent heat, Q is equal to mass times latent heat of fusion in this case, because you're melting. Okay, the mass is the same iron that's melting, so the mass will also be 0.001 kilograms. Okay, we want to find latent heat L, so that means we need to rearrange this equation to isolate L. L is tied to the mass via multiplication. That means we need to divide by the mass. We have to do the division on both sides. And therefore, you have L is equal to Q divided by M. So to find the latent heat, you have to figure out how much heat is added during the phase change. Okay. Right, so during the phase change, so just like we did before, Q is equal to 5 joules every second. So we need to figure out how long you've been adding the heat in order to find the total heat that was added during the phase change. So that's only between the time interval 136 and 190 seconds, right? So we can write down here 5 joules of heat is added over the time interval of 190 minus 136 seconds, right? Or that's a time of 54 seconds. Okay, does that make sense? Right, so the phase change occurs only between 136 and 190 seconds. So that means 54 seconds. So over 54 seconds, you're having that phase change and you're adding 5 joules every second. So therefore, the total, so the energy or the heat added during phase change will be 5 joules times 54 seconds, because you're adding 5 joules every second for 54 seconds. So that's a heat added of 270 joules. All right, so the latent heat of fusion is therefore 270 divided by 0.001. 270,000 joules per kilogram. All right. Okay, so question G is sort of similar to question, what's this? Question E. Except that this time it's just purely liquid iron. In question E, it was solid iron, but the concept is the same. So we're being asked to determine the specific heat capacity of liquid iron. Okay? And we've identified earlier that region C is when iron exists as a liquid only. And so any heat added to that liquid iron goes into the increase in temperature of liquid iron. Okay, and that goes on over this time interval from 190 seconds to 250 seconds. So that's a time of 250 minus 190, 60 seconds. Right, so over those 60 seconds, any heat that's added to liquid iron goes into increasing its temperature from 1,535 degrees Celsius to 1,900 degrees Celsius. Right. Okay, so change in temperature and heat, they're related through this equation. Q is equal to mc delta T. Again, we're being asked to find C, which we've rearranged. We've rearranged this equation earlier, so it will be the same rearranging. And so to find C, we need to figure out Q, and then divide that Q by mass times delta T. So mass, it's the same iron, so it's still the same mass, 0.001 kilograms. Delta T, okay, we're looking at region C, liquid iron. The temperature changed from 1535 to 1900. Therefore, the change in temperature, T final minus T initial, so 1900 minus 1535. That's a change in temperature of 365 degrees Celsius. It's also 365 Kelvin for the change in temperature. Okay, now for Q, right? 5 joules, we need to find Q. 5 joules of energy is added to the liquid iron over the time of 60 seconds, right? Between the time intervals 190 seconds to 250 seconds, you're adding heat to the liquid iron. So that's a time of 60 seconds, right? So the heat that's added over 60 seconds will be the rate for which you're adding heat, 5 joules every second, times how long you're adding that heat. So 5 times 60, 300 joules. Okay, so then you can solve for the specific heat. It's equal to the heat added, 300 joules, divided by the mass, 0.01, times the change in temperature, 365. That gives you a specific heat of 822 joules per kilogram degrees Celsius, which is also the same 822 joules per kilogram Kelvin, because change in temperature, 365 degrees Celsius is the same as 365 Kelvin. All right, and finally, how long will it take for the solid iron to be fully melted if the mass is doubled to 2 grams? So the rate of energy input is still the same, 5 joules per second. Okay. In the previous question, in question D, Okay, we already said that it takes 190 seconds for 1 gram of solid iron to be fully melted, right? 190 seconds for 1 gram. Fully melted. Right? Keeping everything the same, meaning same input, and it's the same material, of course. Same energy input. Okay. If you doubled the amount of iron, okay, then what happens to the time it takes to fully melt it? Will it also double, or will it take you or will it have, or will it be some different random time? What do you think? Right? You can think about this logically, say get yeah, double. Yes, so I can see there an answer that says double, but yeah, you can think about this logically. Say you boil a cup of water and it takes you 1 second to boil that cup of water. Maybe not 1 second, maybe 10 seconds. So you get a cup of water and it takes 10 seconds to boil that cup of water, right? If you do the same thing, like after some time, you take another cup of water and boil it and boil it using the same kind of pot and the same heat settings, it will also take you 10 seconds to boil another cup of water, right? Okay, so that tells you that if you double the amount, then you also double the time, keeping everything else the same amount of energy imparted in the same material. Okay, yeah, so you're right. You're right, and you can solve this intuitively. You can answer this intuitively. If you double the amount, then the time would also double, keeping everything the same. Okay, so that means double the amount, 2 grams will take 190 seconds times 2, or 380 seconds to fully melt the iron. Okay. Cool. Right, and that ends, we've answered all the questions in the worksheet, so that ends the workshop. Unless you have any questions or if you need to clarify something, I'm happy to do that as well. All right, if there are no questions, then we can end the workshop today. I'll be online at 1 o'clock if you want to go over something or you have any questions, but I'm also available via email. Okay, so otherwise, have a great weekend, everyone, and I'll see you again next week.